Swayam Prabha. Digital India. Educated India.
Hello students, let us continue our discussion on the condition of spontaneity and equilibrium during a change in state of a thermodynamic system, and we are doing so in terms of thermodynamic potentials. We have already seen that we are trying to have a generalized condition of spontaneity and equilibrium, but for that we started from the second law of thermodynamics and combined first law with it and said in an isolated system, you can derive this condition either in terms of entropy or in terms of internal energy change during the proposed change in state. And when we generalize this condition for spontaneity and equilibrium for both non-isolated and isolated systems, we do so in terms of some energy functions which in general we call as thermodynamic potential. And I have already shown to you that there are several different energy functions that we come across in thermodynamics. The first one is called the internal energy. The second one is called the Helmholtz free energy. The third one is labeled as the enthalpy, and the fourth one is labeled as the Gibbs free energy. As you see here that I have used these four different energy functions in four different contexts. This basically answers the question as to why do we need so many energy functions in thermodynamics? The idea is as follows. Depending on the kind of experimental setup that you have, you can have either an isolated system or you can put the system in thermal equilibrium with a thermostat so that its equilibrium state is defined in terms of these three variables. Or if it so happens that you have a system which is otherwise isolated, but one of its walls, in spite of being adiabatic and impermeable, is movable and is connected to a barostat. So in that case, the system will be at equilibrium with a pressure reservoir or a barostat, and its equilibrium state will be defined by specifying the value of entropy, pressure, and the number of particles. Now, if the system is in thermal and mechanical equilibrium with a reservoir which operates as both a thermostat and a barostat, in that case, how do you characterize the equilibrium state of this system? Then I find that it is most useful to determine the equilibrium state of the system by giving a specific value of T, that is the temperature of the system, pressure of the system, and of course we are talking about closed systems, therefore the total number of particles would be constant. Therefore, if I want to carry out any change in state, then if I maintain these systems to be closed systems, in that case I understand that I will change, in this case, the value of S from a given equilibrium state to S plus ds, and I can also change V to V plus dV. And now I am looking for an energy function that will directly depend on ds and dV. And I find that du, that is the differential change in infinitesimal change in internal energy, depends directly on ds and dV. And therefore, I would identify internal energy as the thermodynamic potential of the system when it is present in an isolated state. Now let us have a look at the situation where the system is in contact with the thermostat. In this case, my initial equilibrium state may be temperature, volume, and number of particles. And when the system undergoes an infinitesimal change in state, then the new equilibrium state will be defined in terms of T plus dt and V plus dV. Do I find an energy function which depends directly on dt and dV? Here I find that by definition, if F is equal to U minus Ts, then dF depends directly on dt and dV. And therefore, I would say by definition, this F, this is the thermodynamic potential of the system which is present in equilibrium with the thermostat. And since any given equilibrium state of the system is characterized by a given value of temperature, volume, and the number of particles, then F will also have a value specific to the equilibrium state of the system, as it is a state function, and therefore it is going to be a function of T, V, and N. So now if we think of the system in thermal equilibrium with a barostat, in a mechanical equilibrium with a barostat, I find that the new equilibrium state can be defined in terms of S plus ds and P plus dP when it undergoes a change in state. And associated with this change in state, I have one energy function H, which is defined like this, where dH depends directly on ds and dP. And therefore, I would say that for such a condition, I must be having H as the thermodynamic potential. Now, if I talk about the system in thermal equilibrium with a thermostat and a mechanical equilibrium with a barostat, then a given equilibrium state is characterized by a given value of temperature, given value of pressure, and anyway for a closed system the number of particles is constant. Now, if I allow this system to undergo a change in state such that T goes to T plus dt and P goes to P plus dP, what is the energy function whose differential variation will depend directly on dt and dP? When I define the Gibbs free energy G as this, I find that dG depends on dt and dP directly. And therefore, by definition, I would say that under such condition, the thermodynamic potential is nothing but the Gibbs free energy. Now, why are these important? So, let us now have a look at the implications to the condition of spontaneity and equilibrium in non-isolated systems, where we have already seen that if I combine the first and the second law of thermodynamics, I must be having this relationship that TdS is greater than or equal to du minus dw. Or in other words, I can always write down that minus du plus TdS is greater than or equal to minus dw. And I have shown in my last lecture that for an isothermal process, I can rewrite this expression as this. So, I have now a variation of the quantity U minus Ts and a decrease in this quantity which must be greater than or equal to the quantity minus dW. Now, under the condition, when I define the Helmholtz free energy as this, then the condition is for any isothermal change in state, the decrease in Gibbs free energy must be greater than or equal to minus dW. Now, what happens if I have no pressure volume work? In that case, I will have dW equal to 0, and then I can very easily write down that in this process, the the Helmholtz free energy will be decreasing, and it will go on decreasing in the direction of spontaneous change. And therefore, this is the first set of condition for spontaneity and equilibrium that we find for a non-isolated system. So I've already taken this example where I have shown you that if this is my initial equilibrium state and this is my final equilibrium state for a chemical reaction, in that case, an isothermal isochoric chemical reaction leads to the direction spontaneously where there is a net decrease in the Helmholtz free energy. Now, let us talk about the second situation where you have an isothermal process, but where it is possible to do both pressure volume and non-pressure volume work. Under such condition, I can very easily write down that if I change the volume of the system by an infinitesimal amount dV, then what is W? W is a sum of the pressure volume work, which is minus P external into dV by definition, and then an additional amount of work, which is once again an infinitesimal quantity and an inexact differential. And this is what I represent here by dW add. Now, if I use this relationship once again in combination with this equation, what can I write? I can write that minus dW plus TdS, that is now going to be greater than or equal to minus dW. Okay, so what I am going to do is I am writing dW as the sum of these two terms. Okay, and then I understand that under isothermal condition, and when I have the constant temperature and constant volume process, in that case, this relationship can be written as minus d of U minus Ts as before. That must be greater than or equal to minus P external into dV plus dW additional. So I have minus dF, that must be greater than or equal to minus dF under constant temperature, that must be minus P external into dV plus dW additional. Now, if I have a constant volume condition, in that case, I will be writing down minus dF dV. Under such condition, I understand that this particular term will go to 0, and therefore, I will be having the condition that minus dF dV is dW additional, which has been written here by just taking the right hand side to the left hand side. So what does it mean? It means that if a system, while undergoing a change in state, has a decrease in free energy, which is minus dF dV, then in that case, I will have the system doing some additional work at the cost of this decrease in Helmholtz free energy. And so when do we know that it is this inequality sign holds? Only when there is an the process is a irreversible one. So when will I have the equality sign? The equality sign is obtained when I have a reversible change in state. Under that condition, we already know that dW is nothing but the maximum work done by the system on the surroundings. Therefore, if my system is doing some work, additional work over and above the pressure volume work, and I am carrying out this process in a reversible fashion, then I can say that my del W max is equal to minus dF dV. If I now integrate these two quantities on the two sides from the initial state to the final state on both sides, what do I get? The left hand side turns out to be minus W max and the right hand side turns out to be minus delta F dV, and have eliminated the negative signs. Now let us take an example which takes an isothermal isobaric process and only pressure volume work is involved and there is no additional work done. Under such condition, I can always say that dW equal to minus P external dV as before. Now, if I carry out this process in a reversible fashion, I can replace P external by the pressure of the system. So, in that case, what I will get is as follows. I use this expression in conjunction to the combination of first and the second law of thermodynamics, and that is what I am going to get. So next what I do is I say that look, I have an isothermal and isobaric process. Therefore, in this case, my temperature is a constant during the change in state and my pressure is also a constant during the change in state. Therefore, I will take this term to the other side and write that minus du plus T of ds, then minus of T of ds, now minus of P into dV, that must be greater than or equal to 0, or I will write du plus d of Ts minus d of Pv, that must be greater than or equal to 0. So if I combine this together, what is the expression that I get? That is the expression that I get over here. So it says that minus d of certain quantity that is greater than or equal to 0 when I have an isothermal isobaric process involving pressure volume work only. Now, do I know what this quantity is? Of course, we can define the Gibbs free energy as U minus Ts, and then I can say that this means that during this isothermal isobaric process, minus dGTP is greater than or equal to 0. Or it means that as the system passes from its initial equilibrium state to its final equilibrium state, then it will go in that direction spontaneously, with which there is a lowering of the Gibbs free energy, and it will stop when dGTP is equal to 0, or in other words, we have hit a minimum value of the Gibbs free energy. Now let us again consider the isothermal isobaric process where I have both PV and non-PV work. So as before, I will write down that dW is equal to minus P external into dV plus del W additional. In that case, what I will do is, this is what I am going to get on the left hand side of this inequality that I have obtained from the combination of first and the second law of thermodynamics. And this must now include the amount of additional work involved in this process over and above the pressure volume work. Now I am going to collect terms which are having contributions of constant temperature and pressure, and I will be able to show that minus del W additional must be less than or equal to minus dGTP. And therefore, when I argue that at equilibrium under the reversible process condition, the maximum work obtainable from the system will be when the equality sign holds, and therefore I can say that W max is delta G Tp. So now let us have a look at the situation that we have talked about earlier. So now I have the reaction vessel, which once again has two compartments, and I have put the blue reactant on one side of a separator in the compartment, and I have the pink reactant on the right hand side compartment inside the reaction vessel. This reaction vessel, I have put it in equilibrium with a thermal and pressure reservoir. So each of the compartments in my reaction vessel, they are capable of exchanging thermal energy and volume with the reservoir, but they are being maintained at constant temperature and pressure. Now, if I remove the constraint that I had here, which is the separator of the two compartments, then the system now finds itself out of equilibrium and a change in state will be induced. And during this change in state, a chemical reaction will be initiated as the blue reactants interact with the pink reactants. And then I will arrive at a final equilibrium state. Then what does the second law of thermodynamics tell us? It tells us that the final equilibrium state is once again maintained at the same temperature and the same pressure as the initial equilibrium state, but that this chemical reaction has happened, it is because in going from this initial equilibrium state to the final equilibrium state, you have carried out an isothermal isobaric process whereby there is a change in Gibbs free energy delta Gp. Now, second law and the first law of thermodynamics together tell you that if during this passage delta Gtp is less than 0, this will be a spontaneous chemical reaction. Now, when will I achieve the final equilibrium state? That is when, during this process, under the given condition of constant temperature and pressure, the system will acquire a minimum value of the Gibbs free energy. Then if you want to perturb the system even more, there will be no further change in the Gibbs free energy, and therefore if I want to perturb the final equilibrium state, I will find that dGTP would become equal to 0. That will confirm the fact that in the final equilibrium state, the given Gibbs free energy has attained a minimum possible value for the given experimental setup. And therefore, now let us summarize the equilibrium condition in terms of system properties. We have seen that the equilibrium condition for an isolated system is that I have this thermodynamic potential U, and if I think about the condition of equilibrium entirely in terms of the system properties, I find that the minimization of U is what decides what would be the new equilibrium state of this isolated system as it undergoes a change in state. If I have a system in thermal equilibrium with a thermostat, there are two ways in which I can define the condition of equilibrium. First, in terms of the reservoir properties, and second, in terms of the system properties. You might ask me, why did I leave this place a blank? That is because in an isolated system, it is not interacting with any reservoir. Therefore, when I am talking about equilibrium in an isolated system, there is no question of mentioning the reservoir property. Now, when I talk about this system plus thermostat situation, what kind of reservoir do I have? I have a temperature reservoir. And I then say that as the system starts from an initial equilibrium state and goes to a final equilibrium state, when does it acquire the final equilibrium? That is when T system, the temperature of the system, becomes equal to the temperature of the reservoir. Under such condition, what happens to the corresponding thermodynamic potential? This actually is associated with the minimization of the Helmholtz free energy. Now you see, if I now in addition to the thermostat, I attach a barostat, and starting from a given equilibrium state, I allow the system to equilibrate in a new equilibrium state, then I find that it does so when temperature of the system becomes equal to the temperature of the reservoir, and the pressure of the system becomes equal to the pressure of the reservoir, and this would be associated with a minimization of the Gibbs free energy. Therefore, let me summarize the observations of this table as: if a system undergoes a change in state under a given experimental condition, then the corresponding thermodynamic potential decreases in the direction of spontaneous change, and it attains a minimum value at the new equilibrium state. Now then we also say that I have designated this as internal energy, but these two quantities as free energies. So now I have two different amounts of free energies. One is the Helmholtz free energy, the other one is the Gibbs free energy. And why do I call it a free energy? That is because this is the amount of energy that is free to do external work. So let us have a look at the definitions once again. A system has a net energy content of U, and usually the Helmholtz free energy is also given the symbol A. So if a system has an internal energy U and it is being maintained at a given temperature T, then U minus Ts is the amount of energy free to do external work. Why is that so? That is because we have already shown that minus dF Tv, that is equal to dW max, and therefore it says that in this particular system, this is the amount that is relevant to computing what is the maximum amount of work that can be extracted for the system. And similar conditions have been seen for the Gibbs free energy, and therefore in that case what we saw was dGTP is equal to maximum additional, and this is also dW maximum additional. And therefore, this is why the free energies are free to do external work. And therefore, now we have the most generic condition for the spontaneity and equilibrium in an isolated and non-isolated system. This is a little cartoon that I would like to show you that would probably give you a very easy way of remembering the spontaneity and equilibrium condition. Little Calvin, the famous cartoon character created by Bill Watterson, said that I find my life is a lot easier the lower I keep everyone's expectations. In thermodynamics, I can just transform Calvin's observation and I say that I find my life is a lot more spontaneous the lower I keep everyone's thermodynamic potential. With this, I will end our discussion on the use of thermodynamic potentials as a general condition for predicting the direction of spontaneous change in state and the final equilibrium state that it achieves. Thank you.